All right, hello. We are going to start with chapter 26, part 1, and we'll be looking at the electromagnetic waves, electromagnetic spectrum, and wave equations. So, the to create an electromagnetic wave, you merely have to wave or oscillate or vibrate a charged particle. And so, if this was a radio antenna, then there might be electrons that would be um, vibrated up and down by an electrical signal sent by your radio station. And as they go up and down, then they would produce an electromagnetic wave. Now, the electromagnetic wave, as we looked at in the last chapter, is created by magnetic fields and electric fields. So you've got your vibrating charges sending these waves out into space. And they can travel, of course, for billions and billions and billions and billions of miles through space, self generating each other as they go. And now, this light is very fast. So we've already seen the speed before, but we'll be talking more about that. Okay, and they regenerate themselves as they go out into space. Now, these have wavelengths, of course, so you can measure the wavelength between two peaks. Okay, but another thing is that this is just a representation of the wave. It's not what it really looks like. What it looks like is, well, when a beam of light hits your eye, that's what it looks like to you. Um, and that isn't what this looks like. But this is a representation that's trying to show you the idea that the electric field and the magnetic field are perpendicular to each other and that it can be larger. But what it means by larger here is not necessarily physically larger. Larger in some places, smaller than others. This is the strength that's being represented. So the electric field is stronger in this location, weaker in this location, and then reverses direction, right? So the electric field and the magnetic field are being represented as the strength of them. And as you go further out from the wave, then it would get weaker and weaker. Okay, but it doesn't actually have a physical limit to it. The wavelength has a dimension, but the electric field itself just goes out until it fades away, which is one reason it's very hard to make a lightsaber because a real lightsaber, just made of light, would keep going forever, right? How do you contain that wave? Okay, so we're going to be looking at the electromagnetic spectrum in several different drawings. So we've already discussed this somewhat. It goes from radio waves, which have the longest wavelength, through microwaves, infrared, into the visible spectrum, and then ultraviolet, X-ray, and gamma radiation, which has the smallest wavelength. And so lowest frequency are radio waves, which is still pretty high frequency. We've got frequencies like 1,000,000 cycles per second. But when you get out to gamma radiation, you've got frequencies of like 1,000,000,000,000,000 cycles per second. So frequency is increasing, wavelength is decreasing as you move from radio waves to gamma waves. Okay, so electromagnetic waves all have the same speed, which is called the speed of light, but you can think of it as the speed of electromagnetic waves. Remember that electromagnetic waves you can abbreviate as EW or EM, sorry. So EM for electromagnetic, and then you can throw waves in there if you want. So anyway, so that's easier to write in your notes. So you could say that speed, the velocity of electromagnetic waves is equal to c. And so c is the symbol that represents 3 times 10 to the 8th meters per second, which is the speed of light and electromagnetic waves in a vacuum. Now, when you're in air, like most of the homework problems you're going to be doing are based in the Earth's atmosphere, you can still use 3 times 10 to the 8th meters per second because the light is still very, very fast through air. There's not much slowdown. Okay, so here's another view of an electromagnetic spectrum, which I kind of like because it's showing how the radio wave, how that size relates to things that we know. So like radio waves, for instance, are about the size of buildings or humans. Microwaves are about 1 centimeter. And so those are getting close to the size of insects, maybe a ladybug. Infrared, you're getting closer at 10 to the minus fifth to the point of a needle. Visible light is about the size of little protozoas. So you can look at those under a microscope, a visible light microscope. But molecules are more the size of ultraviolet rays. And X-rays are the size of atoms. Okay, and a gamma ray is about the size of the nucleus of an atom. Okay, so wavelengths are getting smaller and smaller as frequencies get higher. Now this chart also has a temperature graph on it, which is showing the idea that these different colors are produced at different temperatures, different electromagnetic waves. So we talked about that a little bit when we talked about radiation. And but the idea is, yeah, when you've got things that are warm, so when you talked about temperature, so most objects do not radiate in visible light, they radiate in ultraviolet rays. And I'm sorry, I screwed that up. Infrared. Okay. So most objects on the planet Earth are only radiating in infrared. Only a few things get hot enough to radiate in the visible region. So anyway, so the idea is, yeah, the surface of the sun is about 6,000 degrees, and that puts it right where the visible range is. But most things on Earth are colder, and they are in the infrared range. Now, the visible range is just the parts that we can see. So we've got, so our eyes can see from what Newton labeled as violet, okay, and indigo, which is a deep blue violet, and blue, and green, and yellow, and orange, and red. And notice how the spectrum is not broken up evenly. We've got violet, indigo, and blue all crammed together in this one little area here. And so, yeah, so different cultures have broken the color spectrum into different regions. So some people don't differentiate between blues and greens. It's not that they can't see blues and greens, but they consider them shades of the same color pretty much. And so anyway, so yes, so Newton threw in the indigo and the violet, and or the indigo in between the blue and violet because he wanted 7 colors. We'll talk about this a little bit later. But anyway, this is all humans can detect. There are insects who can see in ultraviolet. So when they look at a white flower, instead they see a design on it that leads them to the nectar at the center. And there are some animals who can detect some infrared, although that's less common than ultraviolet. And red wavelengths are almost twice as long as violet wavelengths. Right? Because here we have the red wavelength. It's about 700 nanometers. And nanometers are 10 to the minus ninth meters. And violet is about 400 nanometers. So yeah, so the red is definitely the longest there. Okay, so here's another thought on the electromagnetic spectrum. is about energy. Energy goes along with frequency. So the higher the frequency, the higher the energy. And so gamma rays would have the greatest frequency, highest frequency, but also the highest energy. Now this spectrum is backwards from the ones we've just been looking at, still perfectly good. And let's look at a typical type question you might have on your homework or a test question. So, which of the following electromagnetic waves has the highest frequency? So, here's a choice of red, green, X-ray, ultraviolet, or microwave. Hold on, let me. Okay, so so which has the highest frequency? Well, we were talking about gamma rays has the very highest frequency, but that's not on this list. So which one is closest to gamma rays would be X-rays, right? So highest frequency, the X-rays. I'll put a C answer there. Okay, which one has the greatest velocity? Well, all electromagnetic waves move at the same velocity in a vacuum. So we would just say all of them. Okay, so all or any are the same. They're all the same. Which one has the longest wavelength? Well, the longest wavelength of all would be for radio waves. But again, that's not on this list. So you got to look for the next longest wavelength. So microwaves, or E, would have the longest wavelength. And which one has the highest energy? Well, highest energy always goes along with highest frequency. So they would have the same answer of X-rays. Okay, so knowing how to rank these according to the electromagnetic spectrum is something that you'll need to know. Okay, so remember I said back in the sound chapters that we would use those equations again. Well, this is the place. So one of the equations you're using a lot is that velocity is wavelength times frequency equation. So you'll be using that. And then, which of course is wavelength divided by period too. But yeah, we're definitely using frequency this time because the period for electromagnetic waves is very, very tiny. So we will generally be using frequency. So anyway, so this equation is going to get used a lot. And so let's do an example. What's the wavelength of a radio wave that's produced by a radio station with a frequency of 600 kilohertz? Now, 600 kilohertz is 600 times 10 to the third hertz. So that's 6 times 10 to the fifth hertz. And it's nice to put it in scientific notation because, of course, we're going to use that equation since velocity is wavelength times frequency. Then we're going to find out the wavelength by taking velocity and putting it over frequency. The velocity for the wave isn't given in the problem, but we know what it is because it's a radio wave. So it's 3 times 10 to the 8th meters per second. Basically, in this chapter, all the velocities are the same. They are c, the speed of light. And then I'm going to divide by the frequency in scientific notation because that usually does make it easier. And that's going to be in hertz or cycles per second. And so what I come up with is 3 over 6 is 0.5. So I do that part first. So 0.5. And then I've got 10 to the 8th over 10 to the 5th. So that's 10 to the 3rd. And so since 0.5 times 10 to the 3rd, 10 to the 3rd is 1,000. So I'm saying like half 1,000. So it comes out to just be 500. And that will come out in meters. Because you'll have meters per second over cycles per second for hertz. So the per seconds cancel, and you get how many meters it is for one cycle or one wavelength. Okay, so anyway, so you're using the same equations you did in the sound chapter. And you'll also be using, remember, the distance equation. So the distance is velocity times time. You'll still be using that in this also. Okay, so let's go on and look at the another example, or at least an idea. AM radio station is in kilohertz. An FM station is in megahertz, or millions of hertz. And so the FM has a higher frequency, right? So we talked about this in another chapter about AM versus FM. And so FM has a higher frequency. And so because it has a higher frequency, it's going to have a smaller wavelength, right? So frequency is bigger, wavelength is smaller. Now the FCC allocates radio spectrums to everybody who wants one and can pay for it, because a lot of these slots you have to pay for, you have to apply for. So you can't just set up a pirate radio station anywhere you want, or at least that's why they're called pirates, because they're stealing wavelengths from others. Anyway, so this is just a small part of an absolutely gigantic chart of the allocation of radio wavelengths. And so you've got ones for mobile phones, you've got ones for TV station, you've got them for weather stations and research, and you've got the Army and satellite data, and everything has a slot that it must go into. So all the excitement about 5G, that was just another opening of another slot to use for communications. So anyway, so no big deal. It's just another slot. However, it is awfully close to some weather satellite data, so hopefully it's not going to screw around with that. Okay, so let's look at visible electromagnetic waves. And this is a great picture because you've got lots of stuff going on. You've got a rainbow, you've got lightning, and you've got just plain sunlight. And so you've got different aspects of light going on here. Okay, so again, the human eye is only sensitive to a small portion of the spectrum. And that's the only one you're really supposed to call light. And these are short wavelengths. You can fit about 10 million across your pupil. And so if you look at a light wave, the wavelength would be about a millionth of a meter. Okay. And of course, different, we do use that unit called nanometers, which is 10 to the minus ninth meters. So we don't have to use negative exponents. And so we talked about how that would go from 400 to 700 nanometers, 400 for violet, 700 nanometers for the wavelength of red light. Anyway, so different wavelengths and different frequencies are seen as different colors. Okay, and that's as far as we're going in this part.